Hello everyone, welcome to the video tutorial of Codeforces round 878. It was a division 3 contest. Here you can see that there were a total of 8 problems in the contest. I felt that problems A, B and C were fairly easy. Problem D was a bit harder than usual. I also felt that problem E was a really nice problem. And again problem G1 was a really nice problem. I totally enjoyed the problem. And we also have G2, so G2 has tougher constraints than G1. So based on that, let's start with the video tutorial.
Hello guys, today we will be discussing the solution to Codeforces round 878 question A. It was a div 3 contest and the name of the question is Cipher Shifer. So the time limit per test for this question is 1 second, and the question statement is as follows. We have a string, we have been given a string S and it is an encrypted string. The encryption happens such that after every letter, suppose I have the letter A, then there would be some garbage letters, let's say B, C, B, D, E, F and so on. But then at the very end of those garbage letters there will be another letter A. So that is how we are encrypting the original string. Now we are given the encrypted string and we have to find the original string. So there are 1000 test cases, and for each test case the length of the string will be at most 100. So we can have an O of n square algorithm that fits well within the time complexity. However, there is a very simple linear time complexity algorithm as well. So here it is. So suppose we have we set an integer flag that tracks the index of unique letters. So obviously the first letter will be unique, so in flag's initial value will be 0. So here is the flag's first value. Then we go on reading the garbage letters, and then we see the same letter being repeated again. So then we update the flag to be the index of this plus 1. So this letter will be the next unique letter or the next letter in the original string, and then we repeat this procedure till the time we reach the end of the string. So as you can see, we are traversing the string one letter at a time, so it is a linear algorithm. So a simple pseudocode for this will be equal to 0 and print s of flag equals s dot find s of flag plus 1 while flag less than length s. So this is a very simple and bare bones pseudocode for this question. So obviously the first letter will be unique, so we print it, and then we update the flag such that we find the next immediate instance of the letter A, and then add 1 to it. Okay, I forgot adding 1. I'm sorry, my bad. So yeah, this will be an O of n time complexity algorithm, and this will print all the unique letters of the string. They're not necessarily unique, they are the letters of the original string. Yes. So this is what the code looks like. So as you can see in the solve function, I first take the length as the input and then the string as the input. Then I set the flag, and while flag is less than the length of the string, I print the letter at the index when the index is equal to flag, and then I update the flag. And after all of this is done, I print a new line because that is the question requirement. And we have to do this while t is greater than 0. where t is where t is the number of test cases that we have. So this was a pretty simple question, and with a very simple solution. I hope you all understood what. So this was a pretty simple question with a pretty simple solution. Thank you all.
Hello guys, I'm Aditya Chan, one of the coordinator of the programming lab IITM, and I'm here to explain you B problem binary cafe of Codeforces round 878 div 3. So let me begin with the solution. Let me explain you the question in short. Basically, you have n coins and you can spend any number of coins less than equal to n. It can be even 0 if you don't purchase any desert. Also, you have k deserts. The cost of I at desert is equal to 2 to the power I minus 1. And the question asks you in how many different ways you can purchase deserts. So let's begin with the solution. Basically, first of all let's calculate what will be the total cost if you purchase all the k deserts. So if you purchase the total cost will be 2 to the power 0 if you purchase the first desert, 2 to the power 1 if you purchase the second desert, and so on up to 2 to the power k minus 1 if you purchase the k desert. So the total cost if you purchase all the k deserts is going to be 2 to the power k minus 1. 2 to the power k minus 1. So basically if you purchase all the k deserts, then the total cost will be 2 raised to the power k minus 1. So now we'll make two cases. Case 1 will be when 2 raised to the power k minus 1 will be less than n. That means less than or equal to n basically. That means even if you purchase all the k deserts, the number of coins that we are going to spend will be less than or equal to n. So yeah, we can purchase all the k deserts. So think of it as you have k blanks. In each blank you have to fill with either 0 or 1. You fill it with a 1 if you purchase the desert, and fill with a 0 if you don't purchase. So basically you have two options for every blank. Either you will purchase the desert or you will not purchase the desert. So for every blank you have two options. So the total number of ways in which you can purchase all the deserts will be equal to 2 into 2 into 2 up to k times. That is equal to 2 raised to the power k. So the total number of ways in which you can purchase all the deserts will be 2 raised to the power k if 2 to the power k minus 1 is less than n. Less than or equal to n. Now let's consider the case 2 of the problem when 2 to the power k minus 1 is greater than n. In this case, if you purchase all the k deserts, then the cost will be 2 to the power k minus 1 and you have only n coins. So you can't purchase all the k deserts. So suppose you purchase suppose you spend n coins. So let's look at the binary representation of n. If you look at the binary representation of n can be written of the form 2 to the power a plus 2 to the power b and so on. Clearly, if you look at another way, it would be like total cost if you purchase the desert a plus 1, b plus 1 and so on. So if you look at the binary representation of n, you will purchase only those deserts at which 1 comes in the binary representation of n. Similarly, if you consider any number of coins less than n, say suppose you want to spend only 1 coin. Suppose if you want to spend only 1 coin, then you will purchase the first desert and its cost will be 2 raised to the power 0. If you want to purchase 3 deserts, if you want to spend 3 coins, then let's look at the binary representation of 3. It will have the form 1, 1, 1, which can be written as 2 raised to the power 1 plus 2 raised to the power 0. So you are going to purchase the desert 1 and the desert 2. If you look at the binary representation of 4, it will be of the form 1, 0, 0, and you are going to purchase the desert number, it can be written as this. So you are going to purchase the desert number 3. So like if you consider any number of coins less than equal to n, you will get a unique binary representation, and for that particular binary representation you will get a unique set of deserts that you can purchase. So in this case you can spend all coins from 0 to n. So the total number of coins in which you can total number of coins which you can spend, total number of different ways in which you can spend the coins will be n plus 1. And since each number of coins is related to a unique set of deserts, therefore there will be n plus 1 options in which you can purchase the deserts. So if 2 to the power k minus 1 is less than n, is greater than n, then the number of options will be n plus 1. So let me sum it up. If 2 to the power k minus 1 is less than equal to n, you can purchase 2 to the power k. There are 2 to the power k different ways, and if 2 to the power k is greater than n plus 1, or so there are n plus 1 different ways. So this is all about this problem. Thank you.
Okay, so we'll do this question C. So basically in this question, what we are supposed to do, we are given an array of length n, and in that array of length n, we are supposed to find continuous subarrays of length at least k, such that the value stored, the temperature of all those elements is less than or equal to q, and we have to find all such possible subarrays. Okay, so the way we'll go about this is, let's say this is the array of size n if you have, and for now let's assume that k equals to 2. Suppose until we'll keep iterating through this array until we find a temperature that's less than or equal to q. So finally we found a temperature less than or equal to q, and from here we'll keep moving on forward until as long as the temperatures are less than q. So we'll have a while loop to check that. And suppose we have this 4-element subarray where temperatures are less than q and k equals to 2. For now, let's assume that. So here 4 is a potential length which will push back in a vector, and we'll continue to check this throughout the array. Suppose somewhere we have a length 3 again, so we'll push back 3. As long as it's greater than k, we'll continue pushing it back in the vector, and throughout the array of size n, we'll find such continuous subsequences which satisfy the given temperature property, and if the lengths are greater than k, we'll push them back. Okay, push them to vector. Okay, so yeah, this is the course vector named lengths which are pushing back, and this is the loop. So as long as the temperature of any element is greater than q, we'll keep moving on in the loop, and when it's not, what we'll do, we'll measure the length of that particular subsequence. So length equals 0, ptr equals I, while ptr is less than n, and so basically this while loop sort of calculates the length, and at the end of it we'll set I to the ptr. So we iterated through the array and we'll set the I is the pointer, the main pointer to the loop, and ptr is just the pointer which we use to iterate through this smaller subsequences. So we'll set I to ptr, and if length is greater than equal to k, we'll push back the length in the vector. So basically this works like an ON algorithm. It's okay. And now once we have this vector in which all elements are lengths greater than k, so let's assume any one element of this vector of say length L, and I can safely say that all possible answers will be either elements in the elements of this vector, the lengths corresponding to elements of this vector, or some kind of continuous subsequence of those. And in this L, we have to find a continuous subsequence of length k, k plus 1, and so on until L, because at least K is what's mentioned in the question. So what we'll be doing is we'll be summing K over K to L, and for any given K, the number of continuous subarrays in this longer array of length L will be L minus K plus 1. I mean, it's kind of easy to see that, like, you kind of put K equals 1, K equals 2, K equals 3, and sort of you see this. Okay, so I'll be splitting this sigma into two sigmas, one from 1 to L and minus 1 to K minus 1. Okay, so in this we are summing over K, right? So L plus 1 is a constant. So this will just be L into L plus 1. The first term of the first sigma. And the second term of the first sigma is basically this minus K being summed from 1 to L. So since we are summing on K, okay, so this won't be 2. The minus L into L plus 1 by 2, because we are summing K from 1, K equals 1 to K equals L. So this is L. And now this second sigma, basically, again, L plus 1 is constant for K. So we'll just have L plus 1 into K minus 1. And for the second term, we are basically summing minus K from 1 to K minus 1. So like N into L plus 1 by 2, that's the formula. Here we'll put N as K minus 1. So we'll have this as minus K into K minus 1 by 2. Basically, we have evaluated the whole expression. So this gives us the answer for any one element of the vector. And once we iterate through the vector, calculating this for each element and sum them, we'll get the total answer. So here, that's what I'm doing. Answer plus equal to, like, these are all the terms. The first term gets simplified to L into L plus 1 by 2, because like this is basically the minus part is just half of the first half. Okay, and then we'll output the answers after summing it for all possible elements. So yeah, that's it.
So welcome to the video tutorial for problem D. There is Wooden Toy Festival. So you can pause the video and read the question. Right. So what is the question here? First thing is we have a bunch of numbers A1, A2 all the way up to AN. Those are the patterns of the respective toys, and in that we should basically find the minimum amount of time it will take, the minimum waiting time, right? So first of all, let's rephrase the question mathematically. So I have a bunch of numbers A1, A2, A3 all the way up to AN. Now first thing is we can sort this. So since we can sort that, let's sort it. Let's also have only unique elements. Why will you have only unique elements? That's because it will make the implementation a bit easier. If you have, let's say, A1 equals A2, it really does not matter because we can just ignore them. Only one of them should be enough. So we'll just ignore non-unique elements and we'll just have unique elements. Now, assuming my set has only unique elements, right? Now, based on this, I have a set A1, A2, A3 all the way up to AN. So let's see what we can do with this. Now, the key thing to note here is the following thing, right? So our aim is to divide this into 3 different intervals. Okay, this is sorted array, remember that. So in each of the intervals, what will be the time required for this? Well, the time required for this will be the maximum in a particular interval. So I'll call this AI2, I'll call this AI1, right? So this AI1 is just A1 really, and I have AI2 also. So AI2 is the rightmost element of the first interval. So how much time will it take? it will actually take ai2 minus ai1, the ceiling of this by 2, right? Basically, you have to divide this by 2 and take the ceiling. So that will be how much time it takes, because let's say there's something like 1, 2, 3, 4. In how much time can we do this? If we choose x to be, let's say 2, if we choose x to be 2, we can always do this in 2 units of time. Like basically, if we choose it to be the midpoint of that interval, we can always do it at most the ceiling of the length of the interval, or length is not the number of elements, ceiling of the difference between the largest element and the smallest element. Now what will be our final answer? Our final answer will be maximum of all of these things. So our final answer will be, in this first interval, we'll calculate how much time it takes. Let's call it t1. Likewise, we do the second interval also, that's t2. So an interval t3. So our final time will be max of t1, t2, t3, right? Okay. Now, so I felt that the answer was pretty straightforward. So we'll do the following thing, right? Let's iterate over I2. So what is I2? I2 is the rightmost, okay, we'll have a couple of indices also. So if I have a sorted array like this, I'll break this here, I'll break this here also. So I'm actually 0 indexing this, so I1 equals 0. I2 is this index, so it is the rightmost element of the first interval. After that, we'll have I2 plus 1. This will be I2, sorry, I'll call this I3. And then I have I3 plus 1 here. And then here I'll have I4. I4 will be actually n minus 1, but n is not the number of elements in the array, it's the number of unique elements in the array, because we already defined it to be unique. So I think that part should be fine. So I have 4 indices, I1, I2, I3 and I4. So what is our task here? Our task is to basically do the following thing. So we want to minimize over all possibilities of I2 and I3. What do we want to minimize? Well, we want to minimize the maximum of I2 minus I1, the ceiling of this by 2. I'll actually take a different color. And then we have a couple of more possibilities also. So here we'll have I3 minus I2 plus 1. And then we have one more thing also, that will be that will be I4 minus I3 plus 1, right? Now once you get this idea, I think it's pretty straightforward. So we'll iterate over all values of I2, right? So we'll just iterate just bluntly over all values of I2. Now if you have a particular value of I2, how will you find the value of I3? So I2 is fixed here, right? So let's say I2 is fixed here. And now what we will do is that okay, right, so we have I2 plus 1, and here I have I4, right? So I have two numbers, I2 plus 1 and I4. So what will be their midpoint? So their midpoint will be just their average, so that will just be I2 plus 1 minus I4 by 2, okay? Now clearly it will be better if the breaking point, that is I3 happened at the average point, it will be very good for us. So if the average point was equal to I3, so at the index I3, if we had the average of I2 plus 1 and I4, that will be very good for us. So that is the basic idea here. So you might know this s dot lower bound function, or even, I mean, anything like a vector dot lower bound function. So we can just do lower bound of, if I call my vector to be A, it will be A dot begin, A dot end, and actually here what should I pass? Here I should just pass the average of I4 minus I2 plus 1 by 2, right? Now like there is a small catch here that it, okay, right, so by the way it should be this minus A dot begin, right? That will give us the index, so that should be I3. There is a small catch here that since lower bound always go to the next index, it could be I3 minus 1 also. So it might be I3 minus 1 also, or it could be I3 also. So it could be either I3 or it could be I3 minus 1. So you have to be very careful about that. And that's it. So I'll just show you my implementation also. The first two times I got wrong answer because of some small error I did. So let's look at the correct solution. So here I have some template stuff. I think you can just ignore that. So I'm just taking an n. So this part is the code that ensures that it's unique. So after this part, A will be unique basically. I'm just getting rid of all non-unique elements, and I'm redefining n to be the size of A. So now A contains only unique elements. First thing is just a small simple implementation thing. If n is smaller than or equal to 3, we can always output 0. Why can we do that? Because if there are only 3 unique elements, let's say they are A1, A2 and A3, I can just choose x to be this, x for the first guy to be this, x for the second person to be this, and x for the third person to be this. And so I can just do it in 0 units of time. So that's why I'm just outputting 0 here, just a small implementation thing. Now here I have some extra code. I guess I didn't use it in the end, so you can just ignore this part, I think. Yeah, so this is something I thought I'll do, but I didn't do it in the end, so you can just ignore that. Now what am I doing? I'm initializing answer to be a very large value. After that, I am iterating over all values of I2. So I2, I'm just iterating between all values of 0 and n. As I told you, I1 we just take it to be 0 and I4 is taken to be n minus 1. So as I told you, I'm taking the lower bound of the following thing. So right. Oh, by the way, this should be AI4 plus AI2 plus 1 by 2. So we're just taking its average basically. So this is the average of like I4 and I2 plus 1. So I'm just taking that average here. I'm just finding the index where that happens. I'm just doing the answer here. But as I told you, the small catch in the implementation that I have to decrement I3 and check once again, because lower bound, if the particular index doesn't exist, like if the particular element doesn't exist, it will move on to the next bigger index. That's why I'm just decrementing it and checking it once again. So that's what this part does. And in then I'm just outputting answer. And as you see, this got accepted. Let's move on with the next question. That is character blocking. So here you can pause the video and read the question. Here we are given two strings S1 and S2, and we are asked to answer Q queries. So basically there are three kinds of queries. Okay, right. So first thing is we are given two strings S and T. We are given Q queries, and the Q queries are of three types. So the very first thing I'll do is the following thing. I'll split this into three parts. Right? I think you will agree with this. Every index can be one of three things. What can every index be? Every index can be either same. It can be same in both S and T. It could be different, or it could be blocked. Blocked means we don't care whether it's same or different. I mean, it could be blocked and same and blocked and different, but I'm saying if it's blocked means we don't care whether it's same or different. So every index should be in one of these three sets. So that's the first property we'll be utilizing here. Now we'll start off by computing the set same and the set different, and of course initially the set blocked would be empty set initially. Now I have three queries, like three types of queries. So let's ignore this T for now. So T is the time for which it's blocked. I'm sorry, I'll call it Ti actually. So Ti is the time for which it's blocked. So let's ignore the time for which it gets blocked for now. We'll come to that later. Right. So if you have query of the first type, what's the query of the first type? It's to block a particular character. So this should be relatively easy. So from the set same, we will erase whatever character it is. So I'll just call the character pause. From same we can just erase pause. From diff also we can erase pause. And then to blocked, I can insert pause. Okay, right. So we have covered the query of the first type. Now query of the second type, what are we doing? Well, we are really swapping any of the two indices. So we're just taking two indices, could be between either of the two strings. We're just swapping those indices and seeing what happens. Now since we're swapping, it's the same thing, right? So let's say the indices are B and D. Okay, so let's say the indices are B and D. So we can be sure that it doesn't need to be the same anymore. So we just do same dot erase B. Likewise, we'll also do diff dot erase B. By the way, erase function, if it's not there in the set already, it won't do anything to it. So I hope that's clear. Same dot erase B, diff dot erase B. Likewise, we'll do for D also. So it should be same dot erase D and diff dot erase D also. Right. Now we have swapped them, right? Now let's just swap them in the string itself. So next thing to do will be just swap the message in the string itself. Now again we'll check in which of the sets they belong. Again we'll check whether they belong in the same set or the different set. So again, this is fairly easy to implement. If Si is equal to Ti, I'm sorry, SB is equal to TB, we can insert it in same. Otherwise we can just insert it in different. If yes means we can insert it in same, no means we can insert it in different. So we're just checking if SB equals TB. Likewise we can do for D also. So you can see that we have done only O of log n operations. Every one of these erase and insert operations are just O of log n. So we don't have to bother about that. Now third one is the easiest one. We have to check if the two strings are equal. When are the two strings equal? If diff dot size equals 0, then they are equal. And if that is not the case, then they are unequal. So that's it. So we have covered all three of the queries. Now let's look at the time thing, because the blocking is not permanent. So like particular index isn't always blocked, but that's actually relatively easy to check. Okay, so let's say we are in the ith query now, right? Ith query, right? So if you are in the, I'll actually write it below to make it a bit clearer. So if you are in the ith query, so let's keep track of an array that actually keeps track of what all indices we did a block operation. Okay, so basically we have an array that array will be, let's say in the fourth query we did a block operation. A4 will be the index at which we did the block operation. So we just define an array at which we did all the block operations, and A4 would be the index at which we did the block operation, right? So I hope that's clear. So we just look at the ith query, right? So if we are at the ith query right now, we will look at the I minus Tith query. So that will be I minus Ti. I told you before itself that Ti is how long the block operation lasts. So we're just looking at I minus Ti and seeing what happens. So if you are having a look at I minus Ti, as I told you, this could be two things, right? So this could either be equal or it could be unequal. So it's one of two things. Either it can be like it could be equal to a particular index, or it could be not equal to anything. So if it's equal to a particular index, the block operation at this particular index will be gone. So I just have to do block dot erase. I guess we called it blocked, I guess. Yeah, blocked. So a block dot erase int. So we just do block dot erase int. Now a particular index has been unblocked now. If it's unblocked, then what should we do? Well, we should check whether that particular index is equal or not. So if sInd equals tInd, then we can do same dot insert in. Else we can do diff dot insert in, right? So I hope that's clear. So I think that will be it for now for this particular problem. So we just have a look at the code also. So same thing I told you, I have two strings here, and then I have three sets as I told you. I've called equal. I mean, here I called it same, I guess, like in this, but here I'm calling it equal. So same and equal are the same thing. So I called it equal in my code here, and also BLK means blocked, obviously. So we just initially inserting them in equal and different, and then this array tims is the array I told you about, in which we check in basically the current minus Ti, whatever was there in the particular index. So this is the part of code I told you that basically that's this part, that is it basically unblocks certain indices. So this part of the code is whatever you can see on my screen right now. So this is the unblocking part, and then this query of the first type, same thing I mentioned, we have to do index minus minus because we are actually zero indexing, so we're doing index minus minus, and then everything I told you about the first kind of query. The second kind of query, which looks a bit long-winded, but actually it's very easy to follow, and this is the third kind of query, right? I hope that makes sense. So let's move on to problem G1. So problem G1 is in search of truth. So you can pause the video and read the question. This is of course an interactive problem, so I think that's very interesting. I felt this problem is my favorite problem, and that's very nice. So right, so let's think about the problem, right? So we have some circle. So in the circle, we have to do the following thing, right? So we start off at a particular index. So we have some kind of arrow that goes like this, and what we can do is we can move this arrow by some k units. So we can move it by plus k, or we can move anti-clockwise also by some amount. So we can move it by some minus k. Now it turns out you can do this just using positive, positive directions. So we won't bother about any anti-clockwise things here. So we'll just do positive rotations here. So we're not bothering about anything else. Now, right. So let's think about the first thing, right? So can you brute force it first of all? So can you do +1, +1, +1 like that? Can you keep doing? And actually the answer is no. Why is the answer no? Because look at n here, n is 10 power 6. But we don't have 10 power 6 queries, we have only 2023 queries. So it's not possible to brute force. So if you just keep on brute forcing, you will not get the answer, and we can't do it. Okay. So instead we have to think of a smart solution. So what's a smart solution? So let's think about this, right? So let's assume the worst case scenario, that is n equals 10 power 6. If n equals 10 power 6, and in every rotation, let's say I'm moving by 1000 units. So every single rotation I'm moving by 1000 units. So I'll be like this, like this, like this, like this. Like this I'll keep on going 1000 times. I'll do that 1000 times unless I hit the initial position. So till I hit the initial position again, I'll keep doing it for 1000 times. If I do plus 1000 each time. Now, what's one very interesting thing to note here? After I'm done with all the 1000 times, I will know what this index is. So, like I know what my initial starting location of the pointer was. Since I know that index, I'll be able to output some answer based on that. So I think that's very important. Now, let's say n equals 10 power 6 minus 1. Okay. If n is 10 power 6 minus 1, what will happen? To make this a bit more clear, I'll kind of zoom this over here. So I'll make 2 more boxes near this. So this is the starting location, right? So this is where I started off initially. Now let's say if I do 1000 plus 1000 queries. So if I do 1000 plus 1000 queries, what will happen? Well, I won't end up at the same position obviously, but actually I will end up over here. Okay, so I'll end up at the next immediate index, and actually that's very nice for us. Like what's a very important thing to note here? So if I do 1000 plus 1000 queries, okay, what will happen is I always will end up between some index between okay, in fact we'll take a simpler case. So let's say for any n that goes from 10 power 6 minus 999 all the way up to 10 power 6. So what's true for all of these indices? For any of these indices, right? I'll erase this. So let's say initially we started off like this. I did plus 1000 and I ended up like this. It's not to scale obviously. So this is plus 1000. Now for any number between 10 power 6 minus 999 to 10 power 6, the interesting thing to note is that I will always land up somewhere here. So I can be sure that I will definitely land up somewhere over here only. It will not be a new index. So I am definitely going to end up there only. Now that's very interesting for us. Why is that very interesting for us? Well, actually that's very interesting for us because I will always end up somewhere in this location only. So I can use 1000 more queries, right? So 1000 more queries of plus 1. So I'll just do 1000 more queries of just plus 1, plus 1, plus 1 like that. And in those 1000 more queries, I have to land up somewhere over here. So I hope that makes sense. So like what am I doing? I'm doing 1000 more queries. In each of the 1000 queries, I'm just finding out what these positions are. Right? So let's reiterate our idea here. So we're doing 1000 queries of plus 1. We're doing 1000 more queries of plus 1000. So in total, we are doing 2000 queries roughly. And our upper limit is 2023. So it barely passes. So it's fine. So we are not at fault here. Okay. Right. Now this of course for only valid for n equals 10 power 6 minus 999 to 10 power 6. But now the most important thing, right? So let's say n was, let's say, maybe let's say 4999, right? So if n was 4999, what will happen? So in my first 1000 queries, I found out every index from 0 all the way up to 999. Right? So I know the values in all of these positions, no issues, absolutely no issues. I know the values at all the positions from 0 to 999. 0 is my initial position, 999 is my is like, so I did plus 1 plus 1 plus 1. So I know all the positions from 0 all the way up to 999. Now the first time I do, like I'll start off at 1000. So technically I'll just okay, so I start off at 1000. Now I'll move on to 2000. I'll move on to 3000 after that. I'll move on to 4000. Now I'll go to 4999. So 4999 might be somewhere over here. Sorry, I mean now I'm doing plus 1000, but n is only 4999, so it will actually overshoot and it will go here. So basically 4999 will be somewhere over here, right? So this is where, so that's where 1 occurs. So we'll be in that particular index, and actually that's very interesting for us. So we actually landed off at an index whose position we know. Like we know that if we hit that particular number, whatever number we hit at that particular point, we will know its corresponding index. So here we are not given the index, but we know what number we are getting, and we know that the numbers we get are unique. So let's say the actual number here, I'll write that in orange color. So let's say the actual number here was 5, actual number here was 7, here it was 8, here it was 9, here it was 4, here it was 2, right? I know that wherever the number I am getting is 2, I know that the corresponding index is 1, and that is good enough for us, and that's it, we are done. So actually in 2000 queries we can always do it. I mean, might be a bit for 2001 or something, but anyways the point is in 2000, like approximately 2000 queries we can definitely do it. And what is the basic idea here? So to phrase this in a mathematical way, we just calculate values from 0 all the way up to 999. Actually 999 is enough. After that I'll see what happens at 1000, I'll see what happens at 2000, and then I'll just keep on going. If I keep on going, what will happen? At some point I will be at an index, right? So at some point, let's say n. So when I hit n will end up being in this interval. So at some point definitely n will end up being in this interval, and that's very good for us. So since at some point n is in our interval, that should be enough for us, and we are basically done. So so I think that's the basic idea. So let's have a look at my code also. So here I have the starting index here. I'm just taking the starting index as the input. I also have this vector here. I'm not really using the vector, so it's just some old thing I had. So we don't have to bother about that. I'm saying that the index of start is equal to 0. I also have a map. So the map gives you all the corresponding indices. So if you are given a particular number, it tells you what is the index of the number. So I hope that's clear. So then here is the 999 queries I told you about. Technically not 1000 queries, but 999 queries, because like we start off at index 0 and we only need up to 999. So we're just taking up to 999 queries. I think that should be fine for now. So I have one more for loop here. Here I'm just outputting 1000 every time. So I'm just doing plus 1000, plus 1000, plus 1000, plus 1000. I just keep on doing that, and I'm seeing what's happening. So in that case, since I did plus 1000 here, oh, by the way, I'll explain this part of the code also. This is if the size is smaller than 1000. So if the size of the loop is smaller than 1000, let's say our size of the loop was 5. Like if we did plus 1, plus 1, plus 1, we'll end up at some index we know already. So if that happens, we'll just output that particular index. So if the size of the entire circle, like if n is smaller than 1000, then this part of the code takes care of that. And if n is greater than 1000, this part of the code should take care of that. So here I'm just if I have an index which already belongs to the map, this part of the code tells you like this reminder kind of, it tells you what is the extra part, like how much more you have to travel, that kind of thing. And here I times mx, that just tells you whether it's like what times 1000. So it tells you whether it's 1 times 1000 or 2 times 1000 or 5 times 1000 or whatever. And so that's the basic idea for this problem. So I hope you enjoy this video tutorial. Make sure to subscribe to the channel, and if you have any doubts, you can post it in the comment section. Thank you.